Hi, I'm Shahnaz. In this lecture, we'll study how one can associate an ideal to an algebraic set. But before that, we'll recall what we did in last lecture. So, we defined the affine space. So, uh, if we have a field K which is algebraically closed, then we define affine n space denoted by a to the n to be the set of all pointers p uh, to be the set of all n tuples, say a1 through an, such that these ai's they are in the field k for all I equal to 1 through n. So this set is called the affine space. Uh, so if we have a polynomial ring in n variables over the field k, and suppose we are given a subset S of this polynomial ring, then uh, the zero set of S is defined as, so it is all those pointers in the affine space such that any polynomial vanish at the point P. So this is true for all, this has to be true for all uh, f in the set S. So this is called the zero set of S. So this is called the zero set of S. Mm, Any subset of any subset of A and of the form ZS. So one can see over here this is a subset of AN. So any subset of the form ZS of AN um, is called an affine algebraic set, or simply an algebraic set. So we have this notation over here. So for a given set of polynomials, so we write z of f1 through fm for this zero set of the set of polynomials containing the polynomials f1 through fm. So this is just a notation over here. So using this notation, uh, so this is what we write for this thing. So using this notation, we have this definition over here. So if f is any polynomial in the polynomial ring whose coefficients are in the field k, so if f is in the polynomial ring, uh, so suppose this is a non-constant polynomial. Uh, then we call the zero set of f uh, to be the hyperspace. This is called the hyperspace. Sorry, hypersurface defined by f. So we have some examples over here. So the first example is that the affine space AN is itself an algebraic set for this AN is the zero set of the zero polynomial, and the empty set is also algebraic set because it is the zero set of the constant polynomial. In particular, it is the zero set of the polynomial 1. So they are both algebraic sets. So this is example first. Similarly, any point P in the affine space is also an algebraic set. So any point P, say this is equal to the n tuple AN in the affine space, so is also an algebraic set. So this point as a set is an algebraic set. For this set P is actually the zero set of the polynomial the polynomials x1 minus a1 x2 minus a2 through xn minus an. So that is why it is the I mean algebraic set. Similarly, if we consider the polynomial equation, I mean for the polynomial y squared minus x cube, which is a polynomial in a2 sorry kxy, while k is the real or complex field. So I mean then the zero set of y squared minus x cube, which is a subset of a2, is an algebraic set. So if we look at the graph of this polynomial equation, so it is like this. So it goes like this, and from here we have this branch. So this is called the so this is an algebraic set called the hospital cubic. Hospital cubic. So we have another famous algebraic set, which is the zero set of the polynomial equation x cube plus y cube minus xy. So the equation for this polynomial is here, y square minus x cube equal to, the equation of this curve over here is this polynomial equation. So this is again a subset of a2. So this is an algebraic set. And it's called, so it is a famous curve, and it is called the folium of Descartes. Folium of Descartes. So it is given like this. So it comes from minus infinity and down to 0 it goes like this, and then it goes to plus infinity. The polynomial equation for this curve is x cube plus y cube minus xy is 0. So this is called, so this is the hospital cubic. This is called the theorem of Descartes. So we have one more curve over here. So it is the zero set of the polynomial equation y cube minus x times x minus 1 times x plus 1. So this is again a subset of A2. It's also an algebraic set. So this is actually a non-singular cubic. So the curve of the geometrical version of this curve is given like this. So it goes like this. So it is like this. So it's a non-singular cubic. So now if f is a polynomial of degree 1, then the zero set of f is called the hyper plane. So let us make this a remark. So if f is a polynomial in the field in the polynomial ring in n variables of degree 1, then the zero set of f is called a hyperplane. Similarly, if there are I mean if n is equal to 1, I mean if we have only one variable and we have a set of polynomials s in the polynomial ring kx such that this zero polynomial is not in S, then zero set of S is actually a finite set. So this follows from the fundamental theorem of algebra. So then Z of S is a finite set. So this means that the affine algebraic subsets of a line or the line and the finite sets. So this means because here the affine space will be A, which is actually a line. So then the sets ZS, which is an algebraic set, are just finite sets and the line itself. So hence, I mean, so hence the affine algebraic sets, algebraic subsets of a line are the line itself and the finite sets. Similarly, if n is equal to 2, then the affine sets other than the empty set and the plane are curves of the, I mean, let us write this down. So if n is equal to 2, then the affine sets, because if n is equal to 2, then we have the affine space A2, which is two-dimensional. So then the affine sets of A2 are affine algebraic sets of A2 are, I mean, other than the empty set, other than the empty set and plane, and the plane are the curves of the form. So these curves will be of the form 0 set of some set, say f, and so I mean, one of the type of algebraic sets will be these curves, and other algebraic sets will be finite sets, and the finite sets of points. For example, if we look at the zeros of the polynomial equation x and y, so this will be the singleton set which contain the point 0, 0 only. Similarly, if we look at the zeros of the set of polynomials x times x minus 1 and y, then the zero set will contain 2 pointers. One is the, I mean, these 2 pointers will be induced by the zeros of these two polynomials. So one will be 0, 0, other will be 1, 0, and the process goes on. Now, we proved earlier that this function z is actually, I mean, which is actually the decreasing function. So what I mean here by decreasing, so we have like we have the situation like this. So we have subsets in the polynomial ring in n variables to the algebraic sets in an. So we have this function z, I mean, to each set s, a subset s here, we associate the zero set of s in an. So this function z is actually decreasing. So the function z is decreasing. So what I mean by decreasing here, uh, I mean it is, that is, if s1 is contained in s2, then the zeros of the bigger set, which is s2, will be smaller than the zeros of the smaller set. I mean, then the zeros of the smaller set will be bigger than the zeros of the bigger set. So this is what I mean by decreasing. So this is what we proved earlier. We also proved that if we have any family of algebraic sets, then their union is also algebraic set. So if S alpha is a family of subsets of the polynomial ring in n variables, then the intersection, then the arbitrary intersection of these algebraic sets is also an algebraic set, because we proved it. This is actually the zero set of the union of these S alphas. So since this is algebraic set over here, this is also algebraic, and this being algebraic means the arbitrary intersection of algebraic sets is algebraic set. We also proved that the finite union of algebraic sets is algebraic set. In other words, also if I take the union of algebraic set ZSI, where and I take this union where this I goes from 1 to n, then this is an algebraic set. For this is equal to the zero set of the product of sets S1 S2 through Sm. Now since this is a subset of the polynomial ring, so zero set will be an the zero set of this set will be an algebraic set. So this implies this is algebraic set. So this shows that the affine algebraic sets are closed sets of some topology on the affine space An, which we call the Zariski topology. Because so this is these affine sets are just closed sets um, with respect to the affine topology. Sorry, Zariski topology. So let us make a remark here. So if we declare these algebraic sets to be the closed sets with respect to some topology on An, so we have the space An, and if we collect all subsets of An whose let's take T over here, Tz. So a set U is in Tz if and only if the set An minus U is an affine algebraic set, then this is a topology on An, and this topology is called the Zariski topology. Now, what will happen if we take a subset X of An? Will that subset inherit its topology from the topology on An? So this is remark 1. So let X be a subset of An, then X inherits an inducer topology, which is same as a subspace topology. Which is same as the subspace topology, whose closed sets are the sets of the form X intersection some algebraic set in An, and any algebraic set in An is of the form Zs, which is Zs for some S which is a subset in the polynomial ring in n variables. So it is called the Zariski topology on n. I mean the subspace topology. Zariski topology on X. In particular, if this X is itself an algebraic set, then the closure subsets of X are precisely the algebraic sets in An, which are which are inside X. So in particular, uh, if X, which is subset of An, is an algebraic set, then the closed sets of X are precisely the algebraic sets of X. I mean the algebraic sets Y in An, which are contained in X, such that Y is inside X. So now we have a short lemma here. So if S is a subset of the polynomial ring in n variables over the algebraically closed field K, so we always mean by a field K an algebraically closed field. So then the zero set of S is actually the finite intersection of algebraic sets, where each algebraic set is of the form Z of Fi, where this Fi is inside S for all I running from 1 through M. So this is M here. Let us prove this. So we denote by this set S along with these L angles the ideal generated by S. The ideal in the polynomial ring generated by S. That is the ideal generated by S contains all the polynomials of the form sigma ai fi, where this I goes from 1 to n such that these fi's are in S and ai's are in the polynomial ring in n variables. This is true for all I. Now by decreasing property, which we mentioned earlier, by decreasing property, since S is contained in the ideal generated by S, so this would imply the zero set of S contains the zero set of the ideal generated by S. Now conversely, let f be some polynomial in the ideal generated by S. Then, by definition of ideal generated by S, this f is of the form sigma ai fi, where I is from 1 to m. These ai's are in the ring, and these fi's are in the set S. So now if X belongs to the zero set of the ideal generated by S, then all the fi's then all the fi's in S, they obviously vanish on X. They vanish at X, and hence so do all polynomials in the uh, ideal generated by S, and hence so do all polynomials f in the ideal generated by S. Now, since this ideal contains the set S, so all the polynomials in set S also vanish at X. So this shows that X is in the zero set of S. So hence zero set of S is same as the zero set of ideal generated by S. Now one can note here the polynomial ring is Noetherian. I mean, since K is a field by Hilbert basis theorem, this is a uh, Noetherian ring, because the Hilbert basis theorem states that if R is a Noetherian ring, then so is the polynomial ring Rx. Then by induction, one can prove that if R is Noetherian, then so is the polynomial ring R adjoined with n variables. So if R is Noetherian, then this is true. Now K being a field, so it is obviously Noetherian. So this means this polynomial ring over here, this is Noetherian. Now if this is the case, then any ideal in this ring is finitely generated. So this is the property of Noetherian rings, that any ideal in a Noetherian ring is always finitely generated. So since polynomial ring this is Noetherian, we have the ideal generated by S is actually the ideal generated by finitely many elements in the polynomial ring, say f1 through f, say fr. So therefore the zero set of the ideal generated by S is actually the zero set of the set of polynomials f1 through fr, which is actually the intersection of zero set of these hypersurfaces. I mean fi's, where I goes from 1 to 1 to r. So this is what we claim it at the first place. Now, the Zariski topology is very different from the usual topologies. So it needs some time to develop an intuition for its behavior. Um, so we should mention this here. So this is a remark, or let us call this a note. So the Zariski topology is very different from the usual topology. The Zariski topology is quite coarse. I mean, it is much weaker. So the Zariski topology is quite coarse. I mean, it's weaker, i.e., it has uh, very few and very small closed sets. If this is the case, it means it has very few but very large open sets, and therefore mm, very few and very large open sets. For example, the non-empty open sets always meet, and hence this topology ceases to be Hausdorff. So the non-empty open sets with respect to Zariski topology so they always meet, and hence ceases to be it ceases to be Hausdorff. So for example, if we look at the three-dimensional affine space, the closed sets are all surfaces, curves, or points. On the other hand, if we look at the usual topology on A3, then all closed balls are closed sets. So, for example, in A3, and the closed sets are all surfaces, all I mean all surfaces, curves, or points. On the other hand, um, the closed sets in A3 with respect to the usual topology are all closed balls. Now, uh, what we want to do, so we have found that to each ideal I mean, so we just saw above that if we look at the sets in the polynomial ring in n variables, we can associate a set in an. So this is the function z. So we take a set over here and we associate with s the zero set of s, which we call the algebraic f1 algebraic set. Now what we want to do, we want to go otherwise. I mean is there any way to take a set in an and to associate an ideal in this set? Now uh, so we can associate an algebraic set, say z of I, with any I in this. So for any ideal I in this polynomial ring, we can always associate the zero set of this ideal over here. But in general, there will be many ideals with same zero set. For example, if I look at the ideal I1, which is generated by the say polynomial x, and the ideal I2 generated by the polynomial x square, then the zero set of ideal I1 is same as the zero set of ideal I2, which is same as the x-axis. So uh, there is this possibility that to two ideals we can corresponding to two distinct ideals, we have the same zero set. Now what we want to do, we want to check whether there is one largest ideal I with a given zero set x, I the set of all polynomials vanishing on x. So that is what we call the ideal of an algebraic set. So we have this definition here. So let x be a subset in the affine n space. So then the set ix, which is given as all polynomials in the polynomial ring in n variables such that the polynomial f vanish at each point p of x. This is true for all p in x. So this is called uh, the ideal of x. So we have not yet proved that this set over here, this is an ideal, but in next lecture we will start by proving this set over here, this is indeed an ideal.